All right, so what we're going to do next is prepare the precinct data. Compile the precinct data so we can run our simulations. So what we need to do first, since there's only mail-in vote, we don't have to worry about different modes of voting here. So we just have to resort this cast vote record by precinct, okay? So we can take all this data right now. Oh, good. We already copied and pasted values. But let's just be sure. Just select the whole thing. Copy it and just paste it over itself. That just makes sure that there's no running formulas. Okay, so now what we're going to do is resort the cast vote record by the precinct. So we're going to do this in a separate sheet. So we're going to make a copy. We're going to leave that as it is for a moment. Because we're going to end up with, we're going to title this now, original, actual election, okay? Okay, this is precincts, okay? All right, so let's go sort this by the precinct. Now, we don't need any of this garbage here. We can get rid of this for what we're going to do. So delete these columns. We don't need this column either. Now let's just keep it there. It's just one extra column. Okay, so what we need to do is create a cumulative total per precinct. So we're going to call this D1 precinct number P J. Can we get rid of J? Oh, here J means the order of the cast vote record when sorted this way. But anyway, D2PJ. We actually have to change, we have to change this to K because now it's in a different order. So J, the J index corresponds to the order of the cast vote record. The K index is the order of the cast vote record when sorted first by precinct and then by cast vote record number. Okay, so let's do that real quick just to make sure. We're going to do that. Okay. And this part is actually pretty easy. It's actually pretty fast. All we need to do is detect when the we're going to get rid of this column. We're going to turn this into a Boolean operator. We'll call this Z or something. So Z of K. What we're going to do say is this starts with does it start with a 1 or a 0? It starts with a 1 actually. And then this will be, so this is going to be Z1 of K. This will be Z2 of K. I'll tell you what the difference is. They're very similar, but they're actually not, you can't imply one from the other unless you do retroactively backwards. So Z1 of K says, is this the first precinct, the first entry for that precinct? Z2 says, is it the last entry for that precinct? Okay. So here we just write, if this equals this, then 0, otherwise 1. Okay, that tells us if it's the first entry. Z2, that tells us we do it this way. We say if this equals the one below it, then 0. Otherwise 1. And this tells us if it's the last entry. We're going to need both of these. Okay. Okay, what we need now, we're going to set this equal to the first row here. Now we're going to write if z1 sub k is 0. So actually, if it equals 1, meaning the precinct changes, then put this cell, okay? Put a money sign before that S. Otherwise, this cell plus the thing above it. And this gives us the running precinct cumulative vote, okay? So when we see the precinct change in the list, which will happen eventually, you'll see that it resets, okay? And it starts retallying the total. Okay, that's pretty much all we had to do. What we're going to do now, we're going to copy and paste over that. And we're going to take this and sort by Z2K. We want to get the last entry now. And we're going to do from largest to smallest. And then we're going to do in P number, smallest to largest. Okay? And that's going to produce the cumulative totals for each precinct in these categories of Trump no, Trump yes, Kamala no, Kamala yes. Just manually scroll down till you see the end of the precincts. There's not that many. Okay. We're going to take this whole chunk of stuff and we're just going to delete it. Okay. Now, let's tell us what this means. Oh. The hell, man? This is Trump no, Trump yes, Kamala no, Kamala yes. Okay, now I guess what we're going to do, we're going to delete all of this garbage. We don't need any of this. We just need the precinct name, the precinct index, and Trump yes and Trump no. Okay? And Kamala yes and Kamala no. Now we need a total. We're just going to add these together. Now what we're going to do is create the hypergeometric distribution array. Sounds really complicated. Trust me, it's not. We only need 3 things here, okay? E, P, 1, EP2, EP3. Okay, EP1 is 65 divided by the total. EP2 is 53 divided by the total, plus EP1. Finally, EP3, this is going to be Kamala no divided by the total, plus EP2. So this gives us our probability. Okay, EP4 is equal to 1. That's why we don't write it. It's always equal to 1. So what's going to happen is each precinct, when we do the simulation, we're going to roll a random number from 0 to 1 And let's say that that number, we'll just do it here, rand, okay? Well, we got 0857 on this roll, okay? So that's greater than EP3. So that would be a Kamala yes vote. But then on the next one, we got 036. That's greater than EP1, but it's less than EP2. So that means we got a Trump yes vote. And over here, we got 0.53, which is greater than EP2, but less than EP3, so we got a Kamala no vote. Okay? So we're doing a precinct level simulation. Okay, so how do we use this? Okay? Well, we have to go over here. And by the way, I'm getting rid of question 6 and Rosen for this example. Okay? Because I don't need that data. All right, so what we have to do here is we're going to... preparing to simulate. Actually, we can do this all in one video. Simulation, okay? So the simulation, I have to create 3 columns here, and I'll explain why. If we were to compare the randomly rolled number, okay, against an offset index in our sheet here. If we were to copy and paste that down a million rows, we would crash the spreadsheet. I know from experience. So what is it that we're going to do then to fix this problem? Okay. We're going to do it one time only. Okay, because remember, we have to run hundreds of simulations. Okay. We're going to write this equals offset. The reference is J1. Put a money sign next to the 1. And then the offset is going to be 0 columns, but the precinct number of rows. That's why we created that custom precinct index. Okay. Now, when you put the precinct number in, put a money sign next to the column. And then when you drag it across, boom. Okay. So let's make sure, let's check this against precinct 6. I have 0.124, 0.299, 0.427, 0.1248, 0.299, 0.527, 0.527. But good. We're going to keep it that way. So we know that this code is working. Drop this down. This is going to be a big operation. Okay. And you might be like, I didn't seem too big. Well, it's really big when you have to do it over and over. We're going to create this as static data. Okay. So now what I'm going to do is, before we do anything, okay, we're going to put the random number. We're going to drop that down. What we need to do now is simulate all of this stuff. Okay? So if we don't simulate this stuff, then we don't know what's happening. Now remember, we kept the undervote there for a reason. We're going to write, we'll deal with that at the end. So if logical test value true. Okay, we're going to write if the random roll is less than this, okay, then 1. Otherwise, if the random roll, just put a 0. Okay. That's it. Here we're going to write if G2, the random roll, is less than I2. Okay. And then we're going to say and. Oh, this is what we're going to do. If this equals 1, then 0. Otherwise, if. Okay. Now we're going to write if the random roll G2 is less than EP3, then 1, then 0. But now we're going to write if, instead of using and, I'm just going to use this. 0 plus this is greater than 1. It's greater than 0. Then 0. Otherwise, okay? And finally, we're going to write if plus equals 0, then 1, then 0. Now we're going to deal with this undervote in a moment. Okay, that's the baseline idea, and then we should never see more than 1 at a time. So here, if we look here, our random roll was 0.58. So that means it's EP3, which means we have no in the orange column. Here, the random roll was 88, which is greater than EP3, so we got a 1, okay, etc. Now we got to deal with this. If this from the original data equals 1, then 0. Otherwise, blah. Okay? If, we're going to do that for each one. If this equals 1, then 0. Otherwise, blah. If this equals 0. Equals 1, 0. Otherwise, blah. Did I do that correctly? Yeah. If 1, then 0. If 1, then 0. And then finally, if this equals 1, then 0, otherwise the original function. So now, you'll see we get all zeros here because there's a 1. That way we're not simulating ballots that weren't even part of the data set to begin with, that we're analyzing. That way the defense can't complain. Between you and me, it doesn't really matter whether you simulate those ballots or not. You're going to get the same result, but it just doesn't leave them any wiggle room to bitch and whine to the judge and try to confuse them. So that's the simulation. We're going to drop that down. And now you can see why we're not running offsets in functions, because if we didn't have EP1, EP2, and EP3 in static form, we would have to be referring with if, thens, else, ifs, and offset functions every single generation, in every single if-then statement that's nested within themselves. Okay? That's when you crash your computer. All right, now this is going to be the county-wide cumulative. And that's the same as before. Set it equal to the first row, and then just add each row to the other row. And you drop that down. Okay. And now we got to do all the same fun stuff. Well, this... And here's the thing, we have to leave this in equation form. We can't copy and paste values anymore. Okay? So Oh, hold on. So Sam, that doesn't make sense. Oh, so this has become B1J. It's going to replace it with this. We know what it means. Okay, it's in the thing right here. Okay, so I'm going to get rid of that. But it's still disjoint. Okay, we just don't need the original list that said Trump, Kamala, yes and no in question 3, which is conjointed, because you already have it in the disjoint form. Okay, Trump no, Trump yes, Kamala no, Kamala yes. Okay. The cumulative total. This is where I meant to do that. I was like, I'm not really sure. All right, so this equals 0, 0, 0, same row. Add to the row above it. Keep time like it is in the next column. That doesn't change. Okay, let's go ahead and do our column sum. We drop that down. Okay, now we need that moving cumulative, right? So we're going to go to our 3% of time, somewhere around here. And we're going to do that whole series that we did earlier in the first video. So we're going to set this equal to the sum of this like so. Do we even need that? Actually, I don't think we need cumulative here, do we? Oh, this simply... Oh, yeah. Yeah, we don't need that either. I know this looks stupid, but... we don't need these either. We're not doing anything. We're not simulating the cumulative here, so we actually don't care what the net cumulative is. Okay, so then, as we're going over logarithms, okay. Then we're going to say this equals the sum from here, K2. Very good. And now, remember we do this plus the sum minus the first cell K2. Send it across. And drop her down. Okay. All right, now we got to go do our logarithms. So let's get rid of this. Okay. And this is the ln of a over b. And this is the ln of c over d. Drop it down. Let's go to 6% of the ballots cast to get our derivative. That's going to be here. Minus, we go up to 3% of the ballots cast. That's the big yellow column. And it's this minus the first entry. Sticks out like a sore thumb. Doesn't have an NA on it. Okay. Go ahead. Drop that down the column. And we've now completed our first simulation. Okay. Now there's a little bit more we got to do there. We have to do the r squared value through psi, which we actually have a very nice function for. That's built into Excel for us. It's a native function. Let's just make sure everything is right. We don't have some crazy looking graph. We should just have an elliptical scatter cloud. Very good. And what you're going to notice is that when we take the linear regression of this gigantic cloud, that we pretty much have r squared 0. Okay, it's like r squared 0.37 or something. But for all intensive purposes, it may as well just be r squared 0. Because in the actual election, if I'm not mistaken, the r squared is like 0.85. So trying to get a smaller, like the smallest possible pixel real quick. Well, anyway, there's a million data points there, but each one is really a point. But if I were to, let's just regenerate the simulation real quick. You could just put in a random number anywhere. It's dynamically uploaded. And, the slope might get a little less, a little more. Maybe we'll go negative, positive. Whatever it turns out to be, okay, it's just the r squared value is always going to be pretty low, okay? Like you just don't get parallel movement between parties, especially when we have to do this on a psi scale and not on an r squared. So, r squared 0. Things like that, If we were to look at time versus the logarithms, just to give you an idea. That way you're not wondering like maybe potentially what this does or doesn't look like compared to the actual election. So here's the thing, like that r squared of 0.9, like maybe it kind of looks scary to you. Like, oh no, could that mean that r squared of 8.3 could be possible? No, because r squared was never the correct way to measure it to begin with, okay? Like here's r squared 0.15. You always have to use the logarithmic value because that's the only normally distributed metric. R squareds are not normally distributed, okay? So I'm not scared that I'm seeing 0.15. Okay, I'm not even remotely scared when I see that. I know that we're never going to see r squared 0.83 or 5 or whatever it is in the actual election. Okay, there's an r squared 0 for you. So here's what we get here. And if we compare that against the actual election, and you might be like, well, I really can't see much of a difference here, right? But what it really ultimately comes down to, as you know, is the r squared value of their derivatives. That's the only thing that actually matters. Okay, so let's put it to the same scale. -1 to 1. Okay. Another thing you'll notice is that this is important too, that the mean and variance of the red and the orange, they're on a different trajectory. So like we have so many ways of showing that this is a rigged election, the actual data. And one of them is just the the mean and variance of blue and orange independent in respect to themselves. Okay, and the other is the general trajectory. Okay, the linear regression of the trajectory against the percentage of ballots cast. Okay, there's so many to smoke these assholes, and I'm probably going to measure all of them for this one. As soon as this wants to comply and give me a positive axis. Oh, you know what I should do? I should put it on manual. Hold on. Give me a second. Go to formulas. Sometimes when you want to do things like this, you just want to put it on manual. So red is how Republicans voted. I think we'll include this too. Yeah, no, we'll include this in our court document. Um, all right, now what we want to do. Actual election. All right, now what I want is the derivative. Okay. I know I want this in black. Black is beautiful. All right. Now here we're going to change from... I'm just going to put time here again. Remember, guys, we simulated this at a precinct level. And in the mail-in vote only, there's no earlier election day votes here. But if they want to say people are supposed to vote the same way in the mail, but differently in election day early, okay, we'll give you that. So we that's what we simulated, and we still didn't get it. ABAD. They'll just keep moving the goalposts forever. So here's the derivative. Now for the simulation, when we do mass simulations, we're not going to have all these graphs and stuff. Obviously, that would be very computationally intensive, but I'm just showing you how to reproduce the graphs, okay, from a single simulation. But we're not in the mass simulation stage yet, okay? We're nowhere near that. We just want to show the judge some basic stuff here, okay? All right, so now this is from U to W to X to Z. I'm just going to do select data. From X to Z. And we're not going to see anything that looks like that. I'll tell you that right now. And then let's get our derivative in there. So this is going to be a big graph, okay? So we have to put this it's sort of like a separate file type thing. And then we'll bring it in later. So this is the simulation. And you're going to sort of get this like fractal looking Mandelbrot thing. That's why we know the R squared just doesn't come out that way. And then we got to do the same thing for the other one, okay? This is really harsh on your spreadsheet. I just want to let you know that in advance. Like this makes this will make XL explode. Type thing. Especially when we go and rescale it. Okay. So we're just going to put the bounds negative. Well, no, it depends on what the boundaries of this is, actually, isn't it? So this is graphing the derivative versus the derivative. And yeah, I mean, that's pretty big, right? Anyway, let's just do this in square. So we're going to go -4 to 4. Well, maybe we go 6. Negative. Yeah, we're going to do it in square. You know, we'll go 5. We'll go 5 to 5. Even though we'll lose a few data points. It's fine, I think. Alright, so the point is that this is now in square. Okay. Now we're going to draw this one to the same scale, okay? So we're going 5 to 5. And you're going to see a huge, huge difference here, okay? And if we can get our trend line, let's get it in green. We'll make it a good 10-pointer. Do the same thing here. Make it green. Make it another 10-pointer. Hey, Alice.
Yeah.
Can you see the difference between a fair and a rigged election?
Yeah.
Now, hold on. I'm going to show you the parallel movement as soon as Excel stops fucking crashing. Here, look.
Okay.
That's the rigged one, the actual election.
Oh, yes.
That's what a fair one looks like, where they're just weaving in and out of each other at random.
Right.
Here's the overall trajectory. There's a fair one.
Okay.
All I did was take their own totals in each precinct. I just said how many, Trump yes, Trump no, Kamala yes, Kamala no votes there were from their
Okay.
own data.
Okay. It's completely different.
Right.
Yeah.
Listen, took their own data, their own finalized precinct totals.
Right.
So let's say you had 10 Trump yes votes, 20 Trump no votes, 30 Kamala yes votes, and 15 Kamala no votes.
Right.
I roll a random coin from 0 to 1, and wherever that lands tells me if it's a Trump yes, a Trump no, or Kamala yes, or a Kamala no vote based on the actual election result in the precinct. So I just simulate that. So I get the same overall general result as the election in the final totals, but the trajectories don't look anything like the actual election
No.
or anything like a previous historical election. You know what previous historical elections look like? They look like that.
Right. Right. Going back as far as 2016?
And now here, what you see in this plot is the correlation between the changes. So in the actual election, there's a very strong correlation between the changes in Democrats and Republicans. In the simulation, there's no correlation.
None at all.
R squared 0. That means no correlation.
I see. It's the proof is in the pudding.
Yep. Anyway, guys, so that shows you how to set up the graphs. And then we're going to go to the next video. We'll be setting up mass simulations. So we're going to get rid of all these graphs and stuff we don't need. Anything we don't need, we get rid of for the mass simulations because it's too computationally intensive. We have to redo. We even have to get rid of cell formatting, like the red, blue, green, yellow, brown, all of that. The font, everything just gets set to default, so Excel doesn't have to think about anything except the mass simulations. Okay.